So hi everyone, I welcome you all to this ninth lecture where we will be containing mechanical properties of fluids. And so far we have discussed a lot of fluid statics. So yesterday I was about to complete the fluid statics. Only one thing is remaining, that is Pascal's law. And before Pascal's law, I gave you one numerical. So let's look at the solution of it. So this is the previous year, I guess previous year question. I don't exactly remember, but this is a very nice question. So a cube of wood supporting 200-gram mass just floats in a water. So a cube, so there is a water and a cube that is completely immersed according to question. So this is a cube and above it there is a 200-gram mass. Okay, that is supported by the. So this is the configuration at t is equals to 0. When the mass is removed, the cube rises by 2 centimeters. What is the size of the cube? Let's say initial height of uh, this block is x and this is of 200 gram. If we removed it, the new configuration is like this. The cube rises by 2 centimeter. So this length is now 2. This complete length is we have taken it to be x. This is 2 centimeter rises above the liquid. The important thing is it is floating. So in both the cases, F net is 0 according to law of flotation. It is in equilibrium. So in the first case, let's make a free body diagram to it. So for the first case, there is a weight of block plus weight of wood. There is a weight of block plus weight of wood. Upthrust is acting like this. So here the equation comes out to be WB plus W wood is equals to upthrust. So weight of uh, this this block is 200 gram. 200, let's put it in gram into 10, that is G, plus weight of wood, that is rho of solid into volume, that is area, has some area, and X is equals to upthrust is density of fluid, that is rho F, let's say, and it is water. It is not given, but as it is water, so let's take it 1 gram per cc. So rho F we can take to be 1 gram per centimeter cube into, it is completely immersed. So what is the displaced water? That is X into A. Okay, so this is density, this is volume into G. So G will cancel out each other. So it will come 200 plus rho S. It's a cube, so it's X square, X cube is equals to, it is also completely immersed, so it is X cube. So it comes out to be X cube into 1 minus rho S is equals to 200. That is first equation. If you make a free body diagram for it, so what we have is, now this weight is removed. So just weight of wood is balanced by the upthrust. So weight of wood is, so that is the complete weight. So rho solid into X cube, and upthrust is X minus 2, X minus 2 into area. Area is X square into rho fluid, that is 1, and G will cancel out from each other. So what we get is rho S x is equals to x minus 2. So rho S is nothing but 1 minus 2 by x. So 2 by x is nothing but 1 minus rho S. And 1 minus rho S we know is 200 by x cubed. So 2 by x is from equation 1, that is 200 by x cube. So x square will go. So x square will come out to be, sorry for this, there is a very less space. So x square is equals to 100. So x is comes to be 10 centimeter. Okay. So x is 10 centimeter. I hope you understand this question. Now let's look at the Pascal's law. One more important question I wanted to discuss, but I will see. I will see it at the end if we have some time. Okay. Okay. So Pascal's law where we started. So according to Pascal's law, force exerted on the fluid elements by its surrounding through direct contact. Sorry. So I have explained two types of forces, that are surface forces and body forces. Apart from that, what Pascal law is? So it states that the external static pressure applied on a confined volume is distributed or transmitted uniformly throughout the liquid in all directions. It is given by Blaise Pascal in 16553. And I have given you this piston example where if you apply pressure at this side, the pressure at this side will be equal. What is different is force and area at both the sides. So here is area is less, so force is accordingly. So we know that AA from here is less than AB. So FA is less than FB in order to have pressure in both the side equal. So let's derive a Pascal's law by considering a wedge. So let's say, so deriving a Pascal's law. Okay. So we need to derive the Pascal law, and what we are considering is considering a wedge shape fluid element. So we are considering a wedge shape fluid element inside a bulk fluid and balance of balance forces acting on it in 3 dimensions. So let's say we have any bulk fluid. Inside that I have taken a wedge or something like this. Okay, so this is a wedge. Let's zoom it out. So take coordinates system like this: x, y, z. So such that this element is dx. This element is, there is a way of taking x, y, z also, but that is not important at your level. So that is x, y, z, and this is dy. And let's take this line to be ds. So here, if I have to take, if this, let's say this angle is theta, then pressure acting at this point is P ds. Normal So pressure is acting normally to this wedge. So that's why it is like this. And we know this angle is theta. So this will become PDS, and this is also theta. This is also theta. So it is, so it's, this will become PDS sine theta, and this component will become PTS cos theta. Why this is important is we want to balance the forces in the y direction and forces in the x direction. So we need to find out forces in the y direction, that is Fy is equals to 0, and forces in the net forces in the x direction, that is also 0. Okay. And similarly, you can do it for z direction also. So from here, if you see, the pressure on this surface, what I call it, this O A B C D. So O D A B. If we are balancing forces in x direction, so we want to worry what is the pressure acting at. So first in x direction, if we are doing, so we want to worry the normal pressure. So the acting pressure acting on face ODAB plus pressure acting on this face normal pressure. So I am not, so the assumption here is one more, that is static system, no external force like gravity. So normal pressure on A C E D is equals to 0. So that is P into area dy into, so this is, let's say, dz, take dz to be 1. If this is dz, so let's take it to be 1 into 1 plus normal pressure on ACED. So that is PDS cos theta, but in opposite direction. So that is minus PDS cos theta. Okay, so that is ds cos theta. So that should be equals to 0. And we know that cos theta from here, that is nothing but dy by ds. So you can replace dy from here. So that will come out to be ds. Sorry, 1 minute. So that is px. That is px. So that is here is. So this is some arbitrary pressure p. Here it is px. In this direction it's px. In this direction it's py, which is balanced out with this arbitrary pressure. So p ds cos theta. So ds cos theta is dy. So px dy into 1 minus p dy is equals to 0. So px should be equals to p. Now do the same thing in y direction. So in y direction, pressure acting on face O, B, C, E plus, that should be balanced by normal pressure in y direction acting on A, C, E, D, and this should be equals to 0. So P y into dx, and these that we have considered to be 1 plus, so that is minus PD as sine theta, that is equals to 0. We know that ds sine theta is nothing but dx. So py dx minus p dx is equals to 0. And so py is equals to p. And from 1 and 2, we conclude that px is equals to py. Okay. So it's two, we did it in 2D. You can also do it in 3D, but if you wanted to do in 3D, then you have to take a wedge, something like this element. I'm telling you, you can try. Do you have a question? Then you can ask. So the wedge should be like this. I have taken sort of infinite in z direction, and that's why it is taken to be unity. The wedge should be like this. And then you are taking a patient in all the 3 direction, and then you can do it in 3D. Okay. So this is all about fluid statics. So before going to fluid dynamics, I wanted to discuss one question. Let's discuss it. That is very important. That's why I cannot leave that question as without a discussion. So I have to discuss that question first. Then we'll go to fluid dynamics. Okay. So that is so before ending fluid statics, I want to discuss one question on that. That is very important question. And then we end our discussion on fluid statics. And then we'll move forward for fluid dynamics. So the question is, so there is water in a tub. So there is a water inside this tub. The length of water is 0.5 meter, and a rod is inclined at an angle theta. So this rod is inclined at an angle theta, and it is balanced by the upthrust. So its weight is balanced. So it is in balanced position. So the question is, at what angle it should be balanced in it? So what is the angle such that this rod, so what is the angle of the rod makes with the left wall of a container so that it will remain in equilibrium position? Options are 45 degree, 60 degree, 100 degree, 20 degree. Take 1 minute. Bit difficult, bit tricky question. But that includes your all the concepts, what you have learned till now. That hint, as a hint I am giving you, concept of rotation is important. Okay, so let's try this question. So as usual, my simple approach is, if you don't know anything, just make a free body diagram. You will get to know something. So that is my repetitive statement, that if you don't know anything, just try to make free body diagram. You will get to know at least something, or you may solve the question correctly. So if this is balanced, let's say consider this. This is at angle theta, that is balanced, and this should be balanced. So its weight in this direction should be balanced by watts. So thrust at this point, so its weight is like this, and upthrust is like this. So weight is the simple concept, weight is balanced by upthrust. Then what's the difficult part in it? So here the question comes, the center of buoyancy and the center of gravity. The concept of center of buoyancy and center of gravity. So always act, weight always act at the, so weight always act at a center, and buoyancy or the thrust always acts, buoyancy or upthrust always acts at the, at or from the center of buoyancy. So that is the important concept. Okay, so that's the important concept, and let's so in this rod, if normal is acting at this direction, then to this angle is nothing but 90 minus. Okay, so there is a normal reaction. So normal, so this angle is, if this angle is theta, so because okay, so there is one mistake that I am going to do. So normal, so there is a, so that is normal to the rod, not the normal or normal reaction. So because it is balanced from here, the normal will go here. So that is the normal reaction. So normal, so if let's say if there is this weight, so if this weight is acting like this, the normal to this is like this. That's the normal reaction. So normal reaction to this is in this direction, and so this is also theta, and this will become n cos theta. So if we make a free body diagram of this, so if let's say this zoomed out point, then what we get is, let's make a free body diagram. So n cos theta, that is normal reaction, plus upthrust in the same direction, that is n cos theta plus upthrust in the same direction, should be balanced by the weight. So, so cos theta you can find out like 0.5, and this, let's say this length is y. Let me take another pen. So this is y. So cos theta is nothing but 0.5 divided by y. Okay, so n into 0.5 divided by y plus upthrust, that is volume, that is in the so it is the upthrust is because of the volume that is displaced by the rod. So y, that is, so let's say the volume of this rod is v, that is inside the fluid, into rho f into g equals to v, complete v, into this rod solid, so that is rho s into g. But the question is, are you able to get the solution from here? There are many unknowns like n, v, vs. Okay, so there are many unknowns. So it is not possible to solve the question at this. But there is another thing that is happening is this rod try to rotate in this direction, and that is balanced by the buoyancy in acting opposite to that. So in that way, let's see, can we do it by torque balance if force balance is not closing the problem, is not closing the problem. So the torque acting And I told you that the torque, how the torque is acting in this. So torque balance is net torque should be 0. And then when net torque is 0, then weight. So weight, I told you, that is the center of gravity. So that is if the length of rod is L, let's say length of rod is L, then this is L by 2, and this, so W into L by 2, and so it's, we need to take its, so torque is always this perpendicular distance from the force. So if this is the force acting at this point, that is center of gravity, then we need to find this distance. So that comes out to be L by 2. If this is cos theta, in this direction, this is cos theta, this in this direction, this is sin theta. So that is L by 2 sin theta. This should be balanced by upthrust into. So now upthrust is the center. So I told you that upthrust is act at the center of buoyancy. Center of buoyancy means to say that the uh, volume of the rod that is immersed in the fluid. So volume of rod that is immersed in the fluid. So that is why by, so this volume is immersed, whose y into area, that is A, and so center of buoyancy is y by 2. Center of buoyancy in this case is y by 2, and center of gravity is L by 2. So that's the difference between two. Keep it in mind. So that is very important for solving this question. This is a bit difficult question. So that is L by 2. So here now upthrust is acting at the center of buoyancy, that is y by 2. And again, this perpendicular distance. So perpendicular distance from here, that is y by 2 sin theta. So can we close the question from here? So one thing is given, that is density of solid, that is 0.5 into 10 to the power minus 3, 10 to the power 3 kg per meter cube. That I forget to write. So let's balance out this. So area into length, that is, so that's the complete weight, because it's weight, L into L by 2 sin theta into G into rho S is equals to, here upthrust is volume displaced. So volume displaced is A into Y into rho F, and it is given, it is water. So density, both the densities are given. So that is water, that is rho fluid into G. So A will cancel out each other. L sin theta will cancel out each other. G will cancel. What we get is, so here 1y is there, and 1 by 2 is here. 2 is also cancelled. So y square by 2. So y square by 2. So that is 1, that is 0.5. So that is y square is equals to L square into 0.5 into 10 to the power 3. And for density of fluid, that is also 10 to the power 3. So y comes out to be 0.5 L, which there is some, we know what is cos theta. So cos theta is nothing but 0.5 divided by y. So we just want y. Am I doing any mistake here? Okay. So I want a length. So length, oh, many things I missed in this question. The length is also given 1 meter. The length is 1 meter, so it comes out to be 0.5. So y is 0.5, so that is 0.5 divided by root of 0.5, and cos theta will become 1 by root 2. So that is theta comes out to be 45 degree. Okay. So the correct option is this. So here the question is, so you have to approach it. So that's a bit difficult question. And the main concept that I wanted to let you know is that when you are balancing torque, keep these things in mind. What are the center of buoyancy and what is center of gravity? So center when it's weight, then it is acting at the center of gravity. When it's buoyancy, it is center of buoyancy. Okay. So that is one important question. Now I will be going to, so that's all about fluid statics. That's all about fluid statics. So now we'll be moving towards fluid dynamics. That's a lot of fluid statics. Now fluid dynamics. Okay, so I will be give you a brief introduction about fluid dynamics and then we'll wrap up the class. So fluid dynamics is where we will be going to study the flow of fluid. Here, fluid is not at steady state. I have already told you what is the difference between fluid dynamics and fluid statics. So here we will be discussing fluid dynamics, the flow of fluid. So fluid is no longer at a steady state. And we will be going to learn about the fluid dynamics of ideal fluid as a part of course. And for ideal fluid, I have told you that we have already discussed that there are some properties that is incompressibility, that is density is equals to constant, inviscid, that is mu is equals to 0, irrotational, there shouldn't be any angular motion inside a fluid. So if you see I don't know, have you ever observed this or not, but there were, if you see this, some river flowing, so somewhere here we have a vortex flow around the river. So it is going like this. So it is going like this. So here, if you put something here, it will go inside, deep inside into the fluid, and you will unable to take it out from here because it is a swirling flow or a rotational flow. But so that's why we are considering. So here, as a part of course, we will be only going to study the rotational flow where there shouldn't be any angular motion of a fluid particle. So I am taking this one example of fluid flow. So here it's a Reynolds experiments. So here what Reynolds did is, so here the fluid is flowing inside a confined channel. And to calculate the velocity, what he did is he inject dye from here and check whether the fluid is laminar or turbulent. So what is the difference between laminar and turbulent flow? That is not much of importance, but just to let you know. So if you see, it's a laminar flow or a streamline flow. So as a part of course also, we will be going to study the streamline flow. So in a streamline flow, if you see as the dye come out of this nozzle, so it looks like a steady state. There is no disturbance in it. But if you see there is a turbulence flow, there is a lot of disturbances, and that's we called as eddies. And this is not a streamline flow. And why it is not a streamline flow? Because so what is a streamline flow or the laminar flow is that the velocity vector is always parallel to each other. That is the, so the tangent to the velocity vector, so it is flowing in this direction, and if the tangent, if we draw a tangent at this fluid, so it will be always be a parallel. So that's why we called it as streamline flow, and these are called as streamlines. So as a part of course, we are only interested in ideal flow and streamline or laminar flow. We will not going to cover the turbulent flow. However, the in many applications where we have uh, I discussed you about the of uh, aerodynamics of plane uh, or the car. So most of them are compressible fluid, and there where there is a turbulence also. So when you are in a jet, you feel when you are in an aeroplane, you feel a turbulence due to the heavy wind. So that is not the part of course. We will be going to start a basics, that is a streamline flow. And tomorrow, uh, so I have some time, I have some time. Okay. So at least I should cover the continuity equation. Okay. So before discussing the continuity equation, so streamline, and just let me write the definition of streamline. So the streamline is one that is tangential to the velocity vector at every point in in the flow at a given instant. The important point to note is streamlines are always parallel and can never intersect each other. So streamlines are always parallel and cannot. So we cannot make the streamlines in this turbulent flow, because you will see that there may be a there will be a streamline. If you try to make a streamline, then they will intersect with each other, and that's why it is not, we cannot call this flow to be a streamline flow. Streamline flow is a smooth flow where streamline are always parallel to each other. So equation of continuity we need to discuss. So as I told you, in all the for all the equations from now in the fluid dynamics, the fluid is ideal plus streamline as well. So let's say we have a pressure driven flow inside this. So there is a pressure driven flow. Area of cross section at this end is A1. Let's call it A2. Velocity is V1, V2. Density is same, rho1. So that rho is same at both the side, and fluid is flowing through this. So equation of continuity tells that rate of mass flow in at one end is equals to rate of mass outflux. It's better to say rate of mass influx is equals to rate of mass outflux. Okay. And also equation of continuity is known to be a mass conservation equation in simple terms. The rate of mass influx is, that is rho density. What we want is rate, because we are looking at the rate. Rate means something per unit time. So that is rho V. We want rho into volume that is going inside per unit time. So in order to make it, we have density into area and into velocity. So this is mass per unit volume, and this is area into length per unit time. So that is AV. So velocity is length per unit time. So that will take care of the rate. So rho A1 V1 should be equals to rho A2 V2. Rho is same because the fluid is same. So A1 V1 is equals to A2 V2. So that's the equation of continuity. Okay. On in more generic way, we can write as AV is equals to constant. But keep it in mind that density is constant. Assumptions are ideal and streamlined. And more important in case of ideal is the density is constant. Okay. So I am giving you one question. Try it at home. That is previous year question of J. So the question is, there is a piston. So area of cross section of this is 8 mm, and okay, and area of cross section here is 2 mm, and piston is moving with velocity 25 meter per second. And when this piston is moving with 25 meter per second, fluid is flowing out from here and it will go here. So the question is, what is the range from this? So what is the range covered by the fluid when it is flowing out of it? So we need to find out the range. Options are options are options are not given, I guess, but I am giving some options: 2 meter, 3 meter, 4 meter. Hint is equation of continuity is needed plus equation of motion. Okay. Try this question. We'll discuss this tomorrow. Okay.